Hi, thanks for joining me today. I'm going to show you a non-standard proof to Euler's formula. So let's quickly recap what Euler's formula is. It says that e to the I theta equals cosine theta plus I sine theta. Okay, now as I said, this is going to be a non-standard proof of Euler's formula. Now the standard proofs use one of two definitions, or at least from my experience, the standard proofs of Euler's formula use the two particular definitions of E. This one here, that e to the z is equal to the sum from n equals 0 to infinity of z to the n over n factorial. And others use this definition here, that e to the z is the unique solution to this differential equation here, f prime of z equals f of z, and then f of 0 equals 1. But there's another definition of e, in that e to the z is equal to the limit as n goes to infinity of 1 plus z over n, all raised to the power of n. And that's the definition of E I'm going to be using today in order to deduce Euler's formula. Without much further ado, let's get stuck in. Okay, so to start this proof, I'm going to be using Moivre's theorem, which says that for any natural number n, we have that cosine t plus I sine t, all raised to the power of n, is equal to cosine nt plus I sine of nt, where here t is just some arbitrary real number. So if you've not seen this result before, it's not too difficult to prove. You just use induction on n, and then you have to use your double angle formulae for cosine and sine. I won't be proving it in this video. It's kind of laborious, but a result that I encourage you just to prove on paper so you're satisfied. We're going to use this guy here, e to the I theta equals the limit as n goes to theta, n goes to infinity of 1 plus I theta over n, all raised to the power of n. So that's just essentially my final limit that I had written on the whiteboard, except with z replaced with I theta, and theta is just some real number. Now what we're going to do is just focus on this complex number here for a moment, 1 plus I theta over n. Now remember, if we draw an Argand diagram, we have our real axis here, our imaginary axis here, and we have some complex number, say z, and it has argument phi and magnitude r. Then we can write z is equal to r cos phi plus I sine phi. Okay, this kind of just almost by definition, but whenever you're introduced to complex numbers, you'll see this result here, and it essentially just comes from looking at using your basic trigonometry. The sine is opposite over hypotenuse, and cosine is adjacent over hypotenuse. Okay, so this is very standard, and I'm going to be using this. What we're going to do is express 1 plus I theta over n in this form here. So firstly, let's work out the magnitude of 1 plus I theta over n. That's not too difficult. The magnitude of this complex number is just the square root of its real part squared plus its imaginary part squared. So this is equal to the square root of 1 squared plus theta squared over n squared. Okay, of course 1 squared is just 1. So it's the square root of 1 plus theta squared over n squared. And what is the argument of this complex number? So the argument of 1 plus I theta over n, well that's just going to be inverse tangent of theta over n. And to see that, let's just go back to our Argand diagram and focus on this complex number, 1 plus I theta over n. It's going to go across 1 and then up theta over n. So this angle here, phi, is just going to be inverse tangent of theta over n divided by 1, which is just inverse tangent of theta over n. So this guy here. So that means that this number here, 1 plus I theta over n raised to the power of n, is equal to, if we do this number here, but raised to the n, so r to the n, but r is just this guy here. So it's 1 plus theta squared over n squared to the half raised to the power of n, which is just raised to the power of n over 2, times cosine of the argument plus I sine of the argument, all raised to the power of n. So that's cosine of inverse tangent theta over n plus I sine inverse tangent of theta over n, and then that all raised to the power of n, like so. Now what we can do is just use de Moivre's theorem to simplify this guy here. Because we're raising this to the power of n, we can drop this n inside the brackets of the cosine, so there's just an n there. So cosine n inverse tangent theta over n plus I sine, squeeze it in just there. It's very small. I sine n inverse tangent theta over n. So if we express the complex number, 1 plus I theta over n to the power of n in this form here. Let me clean up the whiteboard, bring this to the top, and then we'll compute its limit as n goes to infinity, and from that we'll get not De Moivre's theorem, Euler's formula. Okay, so we have 1 plus I theta over n all raised to the power of n is equal to 1 plus theta squared over n squared raised to the power of n over 2 times this long ugly term here, cos n inverse tangent of theta over n plus I sine n inverse tangent of theta over n. Now what we want to do is compute the limit as n goes to infinity of this guy here, and that will give us e to the I theta. So let's work out the limit as n goes to infinity of the magnitude, and then work out the limit as n goes to infinity of the this cos something plus I sine something term. Okay, so let's do this thing here, which is a bit easier. We see that the limit as n goes to infinity of 1 plus theta squared over n squared to the power of n over 2. Well, that's just going to be the same as the limit as n goes to infinity of 1 plus theta squared over n squared raised to the power of n squared. And then that guy there raised to the power of 1 over 2n. Okay, and that's just using standard properties of the exponent in that this guy here to the power of 1 over 2n is just, you can multiply them through to give us an n over 2, which is that guy there. Okay, but the thing inside the brackets is it's quite clearly bounded, because this thing here goes to e to the theta squared, and that's by definition of the limit. Recall that e to the z is equal to the limit as n goes to infinity of 1 plus 1 over n, 1 plus z over n, all raised to the power of n. So of course it's going to work with n squared as well. So this guy here is just the limit as n goes to infinity of e to the theta squared, then 1 over 2n. But of course this guy here is just a constant, and then we're raising it to something which is going to 1 over infinity, so that's going to 0. So this is just some constant raised to the power of 0, which is just 1. Okay, so this magnitude term here tends to 1. Now what I'm going to do is just clear this up and then work out the limits n goes to infinity of this guy here. Okay, so we just computed this limit here. That limit as n goes to infinity of 1 plus theta squared over n squared raised to the power of n over 2 equals 1. And what we want to do now is compute the limit as n goes to infinity of this guy here. But notice that cosine and sine are continuous functions, so we can bring the limit as n goes to infinity inside each of the cosines and sines. So we only really need to compute the limit as n goes to infinity of n inverse tangent of theta over n. And to do that, we're going to have to use L'Hopital's rule, as we'll just see in a second. So we need to compute this limit here. The limit as n goes to infinity of n inverse tangent of theta over n. But quite clearly, as n goes to infinity, this guy here, n, goes to infinity. And inverse tangent of theta over n, well, theta over n tends to 0, and inverse tangent of 0 is just 0. So we have an infinity times 0 situation. So of course we can use L'Hopital's rule by just writing this guy here as dividing by 1 over n. So now we've got an a 0 over 0 situation. So we can use L'Hopital's rule. This is the limit as n goes to infinity. If we differentiate the top with respect to n and differentiate the bottom with respect to n, now normally this isn't valid because n is just discrete integer values, but because we can essentially swap these n's for x's, it doesn't really matter too much. So perhaps I should do that. So that this is the limit as x goes to infinity, firstly, of this guy here. So inverse tangent theta over x now, divided by 1 over x. So this is just now x is a continuous differentiable. X is now a continuous variable, so it takes all real values, as opposed to n, which just took integral values. So we can use L'Hopital's rule because the top and bottom are differentiable, and the top and bottom both tend to 0. Okay, so differentiating the top and differentiating the bottom, we get the limit as x goes to infinity. So differentiating the top, we're going to have to use our chain rule. So this is just the derivative of what's on the inside of the inverse tangent with respect to x, which is minus theta over x squared, multiplied by the derivative of inverse tangent, and then plug in theta over x. So the derivative of inverse tangent is just, so the derivative of inverse tangent of u, say, is just 1 over 1 plus u squared. So plugging in u equals theta over x, this is just times 1 over 1 plus theta over x, all squared. And then we're dividing that by the derivative of 1 over x, which is just minus 1 over x squared, like so. And we're taking the limit as x goes to infinity. Well, clearly this x squared here will cancel with this x squared here, and this minus sign will cancel with that minus sign. So let's just clear things up. This is the limit as x goes to infinity of theta divided by 1 plus theta over x squared, like so. Now clearly as x goes to infinity, this guy here tends to 0, so we've got theta over 1, so of course this limit is just theta. Okay, so the limit as n goes to infinity of inverse tangent of theta over n divided by 1 over n. In other words, the limit as n goes to infinity of n times inverse tangent of theta over n is just theta. Okay, let me clear up the whiteboard and then we'll have to make our final statement and then deduce Euler's formula. Okay, so we've computed these two important limits here and just plugging them back into this guy here, so this monstrosity here, we have that the limit as n goes to infinity of 1 plus I theta over n is equal, or to the n, sorry, is equal to the limit of this guy times the limit of this guy. This guy tends to 1, and this guy tends to cosine of theta plus I sine of theta. Because obviously you can bring the limit inside the cosines and sines, and this guy tends to theta, and that guy tends to theta. Okay, so we get that the limit as n goes to infinity of 1 plus I theta over n equals cosine theta plus I sine theta. But remember, this guy here, from the start, is just e to the I theta. Okay, so we get Euler's formula. E to the I theta equals cosine theta plus I sine theta, and that is the end of the proof. Anyway, I hope you have enjoyed this non-standard proof of Euler's formula. I hadn't seen it before, and what's quite nice about it is it uses that final definition of E. The E is the limit as z goes to infinity of 1 plus z over n to the n. Yeah, so most of the other proofs are the very standard proof where you just sort of compare Maclaurin series. That uses the definition, the power series definition of E. And then you can also sort of, if you want to prove Euler's formula another way, you can differentiate the function e to the minus I theta times cosine theta plus I sine theta and show that the derivative is a constant, and then that means that the derivative is 0, which means that the original function is a constant, and then just plug in theta equals 0 to work out what that constant is. So those are two very standard proofs, and in fact one of my early videos on this channel I made a non-standard proof of Euler's formula, so I'll leave a link to that in the description below. So it's another non-standard proof, it's not this one and it's not the two I just described, so go and check that out as well. Anyway, thanks for watching this video, I'll catch you in the next one, have a great day.